Hello, 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 everybody, and welcome to Science. Happy Friday. Thank you all for being here on a Friday afternoon. It's going to be a fun one today, okay? Today we are comparing saturations, okay? Continuing our work from Tuesday when we looked at, is there a limit to how much solute can be dissolved in a solvent when you're creating a solution? Turns out there can. It's called saturation, when a solution cannot dissolve anymore or take in any more solute. Here's what you're going to need today: science notebook, pencil or pen. You can also use today's exit ticket on Google Classroom to collect data if you wish, or you can collect it on paper and then transfer that data over to Google Classroom after the lesson is over. And here are our I cans. I can define solution. I can define saturated solution. I can use tools to determine how much solute is dissolved in water, and I can use investigation data to compare the saturations of different solutions. Here's the data table we're going to be using today. I'm going to scoot it slightly closer and tilt it slightly up so you can see everything. There we go. But basically, here's our procedure today. On Tuesday, we looked at different salt water solutions, salt being the solute, water being the solvent, the thing that gets dissolved into. And we found that at some point, the more and more salt that you add, it stops dissolving, and excess salt collects on the bottom of the container, in this case, because salt is denser than water. So we found that there is a limit. Solute won't just keep dissolving and dissolving and dissolving forever, right? The analogy I kind of want to use is like a concert, right? Let's say like a BTS concert or something. The solvent is the arena, the solute are the fans. And at some point, that arena is going to sell out and fill up, and there will be no more room for any more people, and they will be very, very sad because they can't listen to their K-pop. And yes, that is my one old man teacher tries to be young and hip with a recent reference for the month. You're welcome. So this idea that at some point, your solvent won't be able to take in, there will be no more room for your solute, and your solution will be saturated because it's full up, okay? What we want to look at today is, do different solid materials have the same level of saturation, right? If, yesterday we saw, I think our sample was about 22 grams of salt in 50 milliliters of water, and we're going to retest that today just to make sure. We might have ended up with a little more or less than 50 milliliters of water, so we want to be sure and see. Will different solutes dissolve in the same way and end up with the same point of saturation? Okay, so here's what we're going to use today. We have our control, which is just going to be water, just 50 milliliters of water, weighing out to 50 grams. Okay, we have our salt from, these are in alphabetical order, these three. We have our salt from Tuesday. We're going to test that one again, just to get a fresh sample to see how we did. We also have two other solutes today. The first one is called Epsom salt. It says right here, here's my big container of Epsom salt. It says not for human consumption. I will not be tasting the science today, because if I did, there would be no one here to save me. So Epsom salt, often it's used, you might see it as like a healthcare product. Like it has, kind of like what, anti-inflammatory properties, where sometimes you'll like throw it in the bath to like have a soak if your muscles are really sore, maybe. That's kind of what Epsom salt does. You'll often find it in like the kind of the spa section of your local drugstore or whatever. The other thing we're going to test today is called citric acid. Okay, citric sounds like citrus, right? It's sour. If you were to taste it, it would be sour, and what gives a lot of like candies that sour flavor might be a little bit of citric acid, or what gives citrus fruits that sour tartness, right? So here's our procedure. What we're going to do, we're going to measure out 50 milliliters of water. And I left my water on the other side of the room, but that's fine. We're going to measure out 50 milliliters of water. Okay, here's our control. We're going to measure it out. We're going to put it into a separate container here. We're going to add some of our, I'm going to use the Epsom salt here because it's a little bit easier to do. We're going to add enough of our solute that we're going to be saturated. So I'm going to, like, when I'm kind of pouring it in, I'm like going to really overdo it here. If we were doing this in the classroom, we'd go 1 scoop at a time and incorporate until we started to see that evidence that the solution is saturated, which is that there's that excess on the bottom. In this case, I'm just, in the interest of time, I'm just going to do a big dump here. Okay, that I am hoping is going to be saturated. If it's not, I'll be a little surprised because that was a lot of solute I just put in. This particular container has a lid. So we're going to put the lid on, and then to incorporate rather than stirring it, we're going to shake. And one thing that I noticed while I was preparing this investigation was as I'm shaking, what I'm noticing is my hand is starting to get cold. And I was really surprised by this the first time because it was very unexpected. It's something that did not happen with the salt water. But with the Epsom salt, it's getting cold. And if we were doing this in the classroom, you'd be able to feel that this solution is really getting cold. So I looked it up just to see what the heck is going on here. And actually, not only is this creating a solution, but it's creating a chemical reaction where the molecules, the hydrogen and oxygen, in our water and the Epsom salt are, the molecules are actually rearranging a little bit and creating some different things going on. It's not just that they're mixing together, they're actually, creating some sort of reaction at a molecular level, at a chemical level. And part of that is what's called an endothermic reaction, where it's getting colder. The opposite would be an exothermic reaction, where something gets hotter. If you've ever made elephant toothpaste and you'll see it like steaming, right? That's an exothermic reaction where it gives off heat. It's the opposite. It's an endothermic reaction where it feels colder. Really interesting. Okay. Once we've shooken it up, we're going to do the same thing that we did. We're going to do the same thing that we did on Tuesday with our saltwater solution. We're going to filter it out. I've got my little filter thing here with the coffee filter in the top. What we would do is we would pour this in and let it filter through the bottom, okay, and catch it in another container. Spoiler alert, I've already done it because it's not the most riveting internet content if we're just sitting here watching liquids slowly strain through a filter. It takes a few minutes for each one to really filter through. And I felt like that's not a good use of our time, so we're going to keep moving through here. But we're going to filter it through, get out all this. You can see the kind of excess Epsom salts there on the bottom. Okay, that's how we know that this particular solution is saturated. And when we filter them out and get rid of all that solid material, then all we're left with is our saturated solution. So if you haven't done so already, go ahead and copy down this data table. Okay, we've got our 4 different rows here with our control, our citric acid, our Epsom salt, and our table salt. This column says mass of the saturated solution. What we're going to do, once we've filtered it out, and over here, I'll show you in a second, we have our 4 samples that have been, our 4 solutions that are saturated and have been filtered out with any excess, so we get an accurate reading on the mass. And we're going to use our balance to take the mass of the whole thing. So our solute, our dissolved solute, plus our 50 milliliters of water. We know that 50 milliliters of water, and I went ahead and measured it to be sure, does equal 50 grams of mass. The volume being 50 milliliters, the mass being 50 grams. So what we could do is we'll take our total mass of our whole thing, subtract out the water, and what we're left with is the mass of the dissolved solute. Makes sense? Over here, let's take a journey. We have, there they are, we have our 4 samples. And as you can see, they're all clear. There's no excess on the bottom because what I've done is I've already did the process I showed you a minute ago of shook it up, let that solution get saturated, and then filtered out any of the remaining solid material that did not dissolve because it was saturated. So now we have 4 saturated solutions, and well, 3 saturated solutions and 1 control. And now what we're going to do is we're going to find the mass of those saturated solutions. So here we go. We've got our balance here. We have 50 grams of mass already on one side here. Let me go ahead and even this out. Maybe. We're on top of some salt. There we go. Make sure we're even here. Oh, you know what? I was like, why is this not even? It's because there's a thing on one side and not on the other side. Haha. Okay, make sure we're even. And right in the middle there. Does that look right in the middle? I'd say so. Scoot this even closer here. There we go. It's a little bit off to the side there. We're going the wrong way. There we go. Now we look in the middle. Okay. So what we're putting on is a container and 50 grams of weight. Okay. And then here's our control. So this has no solute in it. And it should be, if we got the weight right, look at that. It is right there, 50 grams. Let's just move it a little bit. There we go. So we have 50 grams for our control, okay? Which would make sense because we haven't added anything to it. So we could go back to our data table here. We're kind of moving a lot. Sorry if I'm making anybody car sick. Take some deep breaths. So mass of our control is 50 grams. Mass of 50 milliliters of water is 50 grams. Mass of the dissolved solute is 0 because, well, we didn't add a solute. It's just the water. Okay, now let's start with our citric acid. Actually, before we go to our citric acid, let's start with our salt because we did that yesterday. So here's our salt. Now, as you can see, right, still same amount of water, but because we've added that dissolved solute, it does have more mass. So let's add, we'll start with a 10. So we've already got 50 grams in here. We're going to add 10 more. Moved a little bit, but still heavier on this side. So let's add a little more. Let's add a 5 maybe. Aha. So now we've almost gone past. We've almost got too much. I'm going to take the 5 out. I'm going to replace it with, let's say, 3 grams. 3 of our 1s here. Does that look even? Let's add 1 more. There we go. That looks about balanced. So what we're going to do is we're going to take our weight out. We've got 20, 40, 50, 60, plus 3. So the total mass of the saturated solution, the saturated saltwater solution, would be 63 grams. And I'll let you do the subtraction to figure out how much just the salt weighs. Let's move on to our citric acid. So let's reset here, and I'm going to account for the water with 50 grams. We're going to start with 50. Let's grab our citric acid here. Again, 50 milliliters of water, same water, so all we're really trying to compare is the dissolved solute. a lot heavier? Let's see. Let's start with our 10. Well, that didn't move at all, did it? Let's go another 10. So let's go another 10. Let's go another 10. Whoa, okay, this thing's heavy. Let's go another 10. Still heavier, but we did move there, so that tells me we're close. Let's go with, should we go with a 5? Let's try a 5. My hypothesis is a 5 would be too much, but let's see. Yeah, 5's too much, so we're going to take that 5 back out. And let's go with our 3 again. How do we do there? Oh, that looks pretty good. Maybe even one less. Let's see. That looks pretty close. It looks almost in between the 2 and the 3. You see that? How it went? It's shifted over to the other side when I added 1, but if I take it out, it's not. It's like in between, so we need like a 2.5 almost. We don't have any half-gram chips, unfortunately. So we'll just add a half. So let's see our total mass of our citric acid solution. We had 20, 40, 50, 60, 70, 80, 90, 100, and then we had 2, so 102 grams. Okay, so just to reiterate what we're doing here, because I do see, and thank you for speaking up and get some clarification. So what we're doing here is we are measuring the mass of our 4 concentrated solutions. Okay, and so we first measured our control. Then we measured, oh, that was the confusion. I wanted to start with the citric acid because it's in alphabetical order, but I decided we would start with the salt because the salt is what we did on Tuesday, to start with what we had. And yes, I will write everything down on the whiteboard. So to recap, we measured the mass of the salt, and we found that it was 60, let's try it, let's do it again to be sure. I believe we said 63, but let's find out. 20, 40, so again, this is the salt. Salt, salt, salt. Salt. I'm not adding it to the scale because I don't want to change the weight with the tape. There we go. Salt. Okay, so 20, 40, 50, 60, 61, 62, 63. Okay, so that was the total mass of the salt solution. The saturated salt solution was 63 grams. Okay, now we're going to go to the citric acid. Citric acid. 20, 40, 50, 60, 70, 80, 90, 100. 100 got us close. Let's go by ones. 101, 102, and then it looks close. Maybe go to 103. So somewhere between 102 and 103. Okay, we might even say 103 there. Okay, so citric acid, 103 grams is the total mass of the saturated solution. Okay. Lastly, we're going to go to our Epsom salt. Okay. So here's our Epsom salt solution. Looks the same because, again, it's dissolved. Let's find out the mass of this one. Okay, let's put our 50 back because to account for our water. So 20, 40, 50. Now let's add a 10. Bounced a little. Maybe one more 10 will get us there. Bounce this a little more. Maybe a 5. Ooh, close. We're still a little bit heavier on this side, so I'm going to add a 1. Does that look about even? If we added 1 more, would that tip it too far? I think it would, so maybe we'll go like a half, something like that, okay? So let's count to be sure. Remember, this is our Epsom salt solution. We had 20, 40, 50, 60, 70, plus 5 is 75, plus 1 is 76. So we had 76 grams was the total mass of our Epsom salt solution. So now, once we go back over here to our data, and let's fill it in. So we had our salt was 63 grams. Our Epsom salt was 76 grams. And our citric acid was 103 grams. Now, remember, to find if we have the mass of the whole thing, and we have the mass of the water, what do we need to do to find the mass of just the solute? Right? So being able to, starting down here with our salt, right? 63 grams total, subtract the 50 grams, that's the mass of the water, and then you are left with how much? Okay. Same thing with the Epsom salt, 76 grams minus the 50 grams of water, and then you're left with what is the mass of the solute that dissolved in our saturated solution. Okay, yeah, using subtraction there. So go ahead and fill that in on your own in your data table or write it down in your science notebook. Okay. And then let's think about this. Answer our question above. Will the same amount of solid material dissolve in 50 milliliters of water? Will the same amount of different solid materials? It should be more specific there. The answer is clearly, looking at these very different masses, right? There are different levels of saturation depending on the solute, depending on what you're dissolving, right? And there's a word for that. And our word is, let's see, kind of full up on my space here. So I'm going to write it just below there. Our word here is did I spell that right? Solubility. Might have an A in the middle. No. Okay. Solubility. Okay, the more soluble a substance is, the more of it can dissolve in a solution. Okay, so the higher your number here, the more mass in your dissolved solute, we say that that has a higher solubility, or it's more soluble. If none of it will dissolve, for instance, I don't know, Lego bricks. If we put Lego bricks in water and shook them up, and then filtered them out, would there, would there be any dissolved Lego bricks in water? Probably not, right? So we would say Lego bricks are insoluble because they don't dissolve at all. But these three substances, citric acid, Epsom salt, and table salt, we've seen all have some level of solubility. Okay, so think about which is the most soluble. Which substance had the most mass dissolve into 50 milliliters of water? Which one had the second most? Which one had the third most? Okay. Exit ticket is on Google Classroom, and spoiler alert, it asks many of those same questions that I just asked you here. So if you're not sure, go ahead and watch this on replay, and I bet you can get the answer. And if you didn't watch it at all, then I don't know what you're going to put on your exit ticket. I'll be very interested to see. Okay, thank you everybody for tuning in. Have a good rest of the day. Remember, half of you in the tacos have a writing group meeting in just a few minutes, so you might have to put a pause on your exit ticket and come to writing group and then pick it up later. And then have a great rest of the day today. Have a great weekend, and we will see you next week back with some fresh and hot knowledge for our fifth grade lives. Thank you everybody for tuning in. I will see you soon.